Good evening, students. Okay, so this is a control system class, and we have studied about the basics of control system. So as I told already, control system can be classified into two types. One is open loop control systems. The other is closed loop control systems. In the open loop control system, any open loop control system can be represented by a block diagram like this, and its transfer function is written as g of s, where s is the complex variable. And in general, a control system may have any number of input and any number of outputs. Let's consider a simplest control system that consists of single input and a single output. So to the input terminal, that is the reference terminal, we'll give the reference signal R of s, and at the output terminal we get the response C of s. So the open loop transfer function g of s is equal C of s divided by R of s. Next, closed loop control system. So closed loop control system is also having the open loop block, having the open loop transfer function of g of s. In addition to that, we have an error detector or the comparator, and we have a feedback block with a feedback transfer. So the full block of the system will have a gain that is called as a closed loop gain or closed loop transfer function. So the system is a closed loop system. I'll represent that by using a dotted line, and it has a transfer function. The transfer function is called as now closed loop transfer function, and it is represented by just a T of s or M of s. We can use any of these two symbols. So I'll use T of s. The closed loop transfer function of the system T of s is nothing but again C of s divided by R of s only. It is equal to, as we have discussed yesterday, so g of s divided by 1 plus g of s into h of s. So this g of s into h of s is called as loop transfer function of the closed loop system, or just you write down loop transfer function. Okay. We are going to have more concentration on the open loop systems as well as closed loop systems. Now we are going to learn about the advantages and the disadvantages of open loop as well as closed loop systems. Okay, so open loop systems have some advantages and disadvantages. Closed loop system also are having some advantages and disadvantages. We'll talk about them now. So let's consider now the open loop systems. First, I will talk about the advantages called as pros. First, open loop systems are generally stable. So open loop systems are generally stable. Not all open loop systems are stable. Okay, usually open loop systems are stable. That means according to your input, it will give you output. There will not be unnecessary oscillations at the output signal. So output signal will be there according to the input signal. Oscillations will not be there. That means the system will be stable. Next, open systems need less number of components. That means less number of components. Whenever it is needed, then we can buy them and we can construct a economical system. So open loop systems are simple to construct and they are economical. So they are very simple to construct, hence they are economical. Let's see about the cons now. There is disadvantages. Open loop systems cannot give you accurate output. For example, you have a fan regulator and keep the speed at 1. For example, it should rotate at 100 Why there is no oscillations? Oscillations will occur whenever you have feedback. Whenever you have feedback at certain conditions, you will have oscillations. So we don't have oscillation, we don't have feedback in open loop systems, hence there will not be oscillations usually. Okay. There are some cases at that situation you will have oscillations also. That's what I told. Most of the open loop systems are stable, but not all the open loop systems are stable. Just remember this. Okay. So I will talk about the cons. The open loop systems are inaccurate and unreliable. Inaccurate means what? So you have a table fan, for example, and it is a control system basically. We have a regulator and we press number 1 key, for example. It should rotate at 100 RPM. So instead of rotating at 100 RPM, it may rotate at 90 or 100 or in between these two. Any number you can have. Okay, so we need 100 rotations per minute, but it may not rotate at that speed. Okay, so open loop systems are generally inaccurate, so you cannot rely on them, hence unreliable. Okay. 2. Usually open loop systems are very sensitive to noise. When you do calibration, even if you calibrate instantly, it will go unreliable. Even if you do calibration, that will not be useful for open loop systems. You will not get always accurate output. Most of the time inaccurate output only you will get if it is open loop system. So 100% accuracy, 99.99% accuracy you cannot get. Okay, so open loop systems are very sensitive to external disturbances like noise. Next, open loop systems are very sensitive to aging. So performance of the open loop system systems, okay, degrades due to aging. Aging means here wear and tear. Okay, so due to wear and tear, surely the performance will be varying. For example, you buy a bike, and first 6 months you will have a nice feeling with your bike, and then it starts giving troubles. The performance degrades as you use it for a long time. Okay, so this kind of problem will not be there if you have a closed loop system. So okay, so I will talk about that now. Next, I will talk about closed loop control systems. So I will talk about first the pros. The closed loop control systems are very accurate. That means if you have a regulator with a feedback, that to negative feedback, and if you keep the speed of the fan at 100, so mostly you will find the speed around 100 only, 100, 100.1, 99.9 like that. Okay, so they are very accurate. That is very important for many precise applications. The closed loop systems will be accurate even in the presence of non-linearities. Usually all the components will have some non-linearity. Resistor will also be having non-linearity. Capacitor has non-linearity. Inductor has non-linearity. Bipolar junction transistor has non-linearity. All the components will have some non-linearity. So even though the components that you are having in a control systems are little bit non-linear, if you have a negative feedback and the non-linear system behaves like a linear system, so the closed loop systems are accurate even in the presence of non-linearities. And then the third point, the closed loop systems are very insensitive to noise as well as aging, that means wear and tear. So closed loop systems are less sensitive to noise as well as wear and tear in the components. Most important advantage, that is, any error in the system output can be corrected by the system automatically. So any unwanted variations in the output signal can be corrected by the system automatically. System automatically. This is the very, very important property of the closed loop system. Last, we'll talk about the cons. Cons of the closed loop system. So whenever you have some advantage, due to that, very less, Ganesan is asking a doubt. Less sensitive means what? He is asking. What is the meaning of less sensitive? Suppose assume that I am teaching to you. Okay. Otherwise, I will tell you in terms of system itself. Suppose you are having a audio amplifier that has negative feedback. Okay. So there is a change in power supply. So power supply drops a little bit, or the supply voltage increases up and down. So this will not be affecting the gain of the amplifier. This will not be affecting the shape of the output what you are getting. Okay. So that means what? A system is less sensitive to the power supply variations, less sensitive to the noise. Even if you in the presence of noise, the amplifier will be able to identify the noise and it will reject noise. It picks only the signal and it amplifies. Even if there is age long, you are using the amplifier for very many years, so many years. So even though the components are highly aged, the performance of the amplifier will not be degraded that much. So that's what is called as less sensitive. Highly sensitive to noise means what? It is a bad system. So noise will affect the performance of the system. If the system is less sensitive to noise, means noise will not affect the performance of the system. That's what I have told, that they are less sensitive to noise or less sensitive to wear and tear of the components. Even though components will have some defects, performance of the system will not be affected much. Okay. Cons of the closed loop control systems. First of all, the feedback leads to oscillatory response. Output on the slight change so you need output with respect to time as a constant like this. So you have small oscillations in the output like this. It is acceptable actually, small oscillations. That's what I told. If you fix the fan speed at 100, it will be between 99.9 and 100.1. So slight variations with respect to time will occur. This is because of the nature of the feedback. The feedback leads to oscillatory response. Response means output. Okay. The closed loop systems are generally complex. So sophisticated connections, sophisticated components, many components are needed. So it will be costly. The closed loop systems are generally complex, hence they are costly. Okay. you have negative feedback. So this negative feedback will reduce the overall gain of the system. So negative feedback reduces the overall gain of the system. Next, when you try to construct a closed loop system, it is extremely difficult to make that system a stable system. Okay, so stability is the major issue while constructing the closed loop system. While constructing the closed loop systems. Okay. So while designing the closed loop system, you need to have more care as an engineer. So you need to have more care so that you can make system stable. So to make a stable closed loop system, as an engineer, we need to take more care. More care means the calculations, the quality of the components, all these things should be highly accurate. So we have to have more care in the design and implementation. There are many advantages in the point of bandwidth, in the point of input impedance, in the point of output impedance. So we will talk those things in our analog circuits. We will not be talking all these things here. Okay. So yesterday we have discussed about the transfer function of the system and order of the system. So based on the order, systems are classified into 3 types. Okay. There are certain classes of systems called as first order systems. That means first order control systems. There are certain systems, they are of second order. So second order control systems. And you have higher order control systems. Okay. So even though we are classifying the systems into 3 groups, we will be studying about first order systems as well as second order systems. So studying of higher order systems will not be concentrated because in any book, if you see, they will have first discussion on first order systems and they will concentrate more on second order systems. Automatically you can do in your own the analysis of higher order systems easily, because higher order systems can be constructed by using second order systems as well as first order systems. So second order systems and the first order systems you can attach together and you can get the third order systems, fourth order systems, fifth order systems and so on. So that's what we will concentrate more on first order systems as well as second order systems, and automatically you will have concentration on higher order systems. So first I will talk about first order control systems. First order control systems. So first order control systems are having a typical open loop transfer function as G of S is equal to some constant divided by S. This is a typical or standard model of a first order system. So it has a pole at the origin. The open loop system has a pole at the origin. Okay. Now the simplest closed loop system that you can think is a unity feedback control system. Unity feedback control system will have feedback gain of 1. Instead of H of S, you have just 1. So whatever output you have here, that output will be as it is given to the error director. So here you will have R of s, here you will have B of s, that is equal to 1 into C of s, here you have E of s. Okay, now we are going to find out the closed loop transfer function of the first order unity feedback control system. So this is a unity feedback control system because feedback gain is 1. That means your H of s value is equal to 1. Remember this. So now we will write down the closed loop transfer function. T of s is equal to C of s divided by R of s, that is equal to G of s divided by 1 plus G of s into H of s. So G of s has standard model of K by S. You can write down. So 1 plus G of s has standard model of K by S, and H of s value is 1. Okay, so K by S divided by 1 plus K by S we are having. And you take LCM. So you'll have S into K by S divided by S plus K you are having. So this S and this S will get cancelled. So you have the closed loop transfer function T of S is equal to K divided by S plus K. This model is called as pole zero model or pole zero form of the transfer function. T of S is equal to some constant divided by S plus the same constant. So this form is called as pole zero form. This form of transfer function, so denominator will have poles, numerator will have zeros. So here actually finite zeros are not there. Okay, so pole zero model or pole zero form I can say. Form of the transfer function. So I will plot the pole in S plane. So this is the real axis, this is the imaginary axis. So you have denominator factor as S plus K and equate it to 0. That is the characteristic equation. So S is equal to minus K you are having. So at a minus K you have a pole. Since the system has only one pole, this is called as first order system. This is called as first order system. Pole at a minus K. Okay. Now I'll show you one more form called as time constant form. This is called as pole zero form. I'll show you now time constant form. Time constant form of transfer function. So you take a pole zero form of the transfer function. For this first order system it is K divided by S plus K. So from the denominator factor you take K outside. So you will have S by K plus 1. You are having this K and K will get cancelled. Right. This 1 by K you are having here. I will take that 1 by K as tau. So 1 divided by tau into S plus 1 or 1 plus S tau also it's okay. Where tau is nothing but 1 by K called as time constant of the system. So we'll do a problem here. Find the time constant of the system. So given that, okay, C of S divided by R of S is equal to 50 divided by S plus 10. So we need to find the time constant of the system. Okay. So rewrite the transfer function. C of S divided by R of S is equal to 50 you are having here. You take this in pole 0 form actually. There is a pole at s equal to minus 10. Okay, so take 10 outside, you will have 1 by 10 s plus 1. This 10 and 50 you can cancel, you will have 5 into 1 by 0.1 s plus 1. Now this 0.1 is nothing but time constant. So time constant tau is equal to 0.1 second. Okay. The first order systems have very little applications because the first order system has only one memory element. It could be a capacitor or inductor. Okay, as far as the electrical system is concerned. Now we are going to talk about second order systems. I will show you the previous page. Is it okay? Okay. So we'll talk about now the second order system. Standard model of the transfer function. C of s divided by R of s is equal to omega n square divided by s plus s square plus 2 zeta omega n s plus omega n square. Omega n square divided by s square plus 2 zeta omega n s plus omega n square. This is the standard model of the transfer function where the denominator has a quadratic equation. That quadratic equation, when it is equated to 0, is called as characteristic equation of the control system. Characteristic equation of second order control system. That is a square plus 2 zeta omega n s plus, where this omega n is called as undamped natural frequency. Undamped natural frequency. Okay, and this zeta is called as damping ratio. Okay. So from the characteristic equation, we can get so many informations. So basically, the characteristic equation is a polynomial in S. So that is S square plus 2 zeta omega n s plus omega n square is equal to 0. Okay. So where S is a complex variable. In general, S is sigma plus j omega. But for the system, sigma is equal to 0. So S is equal to j omega. S equal to j omega. This is general definition, but I will take sigma is equal to 0, so you get S equal to j omega. So we'll find out the roots of the characteristic equation. To find out the roots, we are going to use the formula, that is S is equal to minus B plus or minus root of B square minus 4AC divided by 2 into A. So consider this equation. In this equation, the coefficient of A square is nothing but A. coefficient of this S is nothing but B, and this omega n square is nothing but C. Okay, so S is equal to, instead of minus B, you write down 2 zeta omega n. So plus or minus root of B square. So 2 zeta omega n, the whole square with the minus sign, minus 4. A value is nothing but 1 and the C value is nothing but omega n square. Dot by 2 into 1. So you have 2 zeta omega n plus or minus root of 4 zeta square omega n square minus 4 omega n square. Divided by 2. You take 4 omega n square are having. So when you take them common and get outside of the root, square root, so we'll have 2 zeta omega n plus or minus 2 omega n square root of zeta square minus 1 divided by 2. So 2 can be cancelled, and then instead of writing this as zeta square minus 1, I will write it as 1 minus zeta square. So I will get a minus sign inside that, so I will make it j. So if I do it step by step, zeta minus zeta omega n plus or minus, I will write the inside term as minus times 1 minus zeta square. So root of minus 1 is nothing but j. Okay. So now I will write this as minus zeta omega n plus or minus j omega n into root of 1 minus zeta square, where square root of minus 1 becomes j. So the system has 2 roots. So roots, general roots I am writing here. One root is S1. S1 is equal to minus zeta omega n plus j omega n into square root of 1 minus zeta square. Another root is S2, that is minus zeta omega n minus j omega n into square root of 1 minus zeta square. Okay, here zeta is a damping ratio, is a number actually. Square of that also will be a number. Okay, okay. So that number, square root of that number is again a number. So that is multiplied with a frequency. So the frequency omega n multiplied with the square root of 1 minus zeta square is called as damped frequency of oscillation. Damped frequency of oscillation. So remember this. Okay. And the omega n is called as undamped natural frequency. Zeta is called as damping ratio. So system has 2 roots, and based on the location of the roots or the nature of the roots is actually decided by zeta. So zeta is the damping ratio. The damping ratio zeta completely characterize the nature of the second order control system. Completely characterize the nature of the second order control system. So based on that, we'll have classifications. First one. So I'll take zeta is equal to 0. I'll make zeta is equal to 0. When you make zeta is equal to 0, and see what happens. When you make zeta is equal to 0, that system is called as undamped system. If you substitute zeta is equal to 0 in the above equation, where S1 is equal to 0 into omega n plus j into omega n into square root of 1 minus 0 square we are having. And S2, so okay, S1 I will write down, S2 also I will write down, S2 is equal to, so minus 0 into omega n minus j omega n into square root of 1 minus 0 square. So here you get just j omega n, here you get minus j omega n. So you get roots are purely imaginary numbers. So roots are purely imaginary. Roots are purely imaginary and they are complex conjugate. And they are conjugate to each other. So if I draw the poles and zeros, or if I draw these roots on S plane, so this is the real axis and this is the imaginary axis. So this is the origin of the S plane where S is equal to j omega. Just remember S is equal to sigma plus j omega. Just remember this. Okay. Then you have one root at a j omega n. You have another root at a minus j omega n. So for a second order control system, if you find two roots on the imaginary axis, then one root will be negative of the other root. Then the system is called as undamped system. Why this is called as undamped system, we will see later. It is going to produce oscillations. Later we will see about the nature, particular nature. Second case, we will make zeta is equal to 1. We will make zeta is equal to 1. That is called as critically damped system. Okay. So we will substitute zeta is equal to 1 in the equations what we had. So 1 into omega n, that is minus zeta omega n was that, plus j into omega n into square root of 1 minus 1 square. That is going to give you minus omega n plus 0. Then S2 is equal to minus 1 into omega n minus j omega n into 1 minus the square root of 1 minus 1 square gives again omega n. That means you have got S1 is equal to S2 is equal to minus omega n. So roots are real and they are equal. So roots are real and equal. So you have two roots on the same place of the S plane. So this is the real axis, this is the imaginary axis. Okay, so roots are having equal value of minus omega n. There are some systems, they are also called as critical damped system. In that case, you may have roots in the right hand side also, right? In that case, roots can be positive also. We will be discussing those systems later. So roots are real and they are equal. So as in our discussion, roots are getting negative values. Okay, there are systems in which you can have roots that are positive also. They may lie here also. So I am not using that negative term. So zeta value, in general, zeta value can be anything. It can be positive or negative. So later I will tell you about that. Now you just understand. So critically damped system. Third one, where zeta is going to be in between 1 and 0. Zeta is a positive fraction in this case. It could be a negative fraction also. Later I will discuss about that. Now this system is called as under-damped system. Under-damped system. So zeta is a positive fraction. Just remember that. So S1 is equal to, zeta can be anything, 0.7, 0.2, 0.4 like that. So S1 is equal to minus zeta omega n plus j omega n into square root of 1 minus zeta square. Okay, since this zeta square is a small number when compared to 1, square root of 1 minus zeta square is positive. This is positive only. Square root of 1 minus zeta square will be positive. Remember this. So this is nothing but minus zeta omega n plus j omega d. Next, S2 is equal to minus zeta omega n minus j omega n into square root of 1 minus zeta square. Again, this 1 minus zeta square is positive. So you get minus zeta omega n minus j omega d, that is S2. If you see the nature of S1 and S2, they are complex conjugate to each other. They are complex conjugate to each other. And they have negative real part. Negative real part. So roots are complex conjugate to each other. So the real part is negative. Real part can also be positive if zeta is a fraction with a negative value. That is also possible, but we will not have more concentration on those kind of systems, but still we'll solve problems related to that. So you will have two roots. Those two roots are having negative real part in our case, so that is minus zeta times omega n. Then they are having imaginary part that are equal and opposite. One is j into omega n square root of 1 minus zeta square, other is minus j into omega n square root of 1 minus zeta square. So roots are having negative real part and they are complex conjugate to each other. So this kind of system is called as under-damped system. This system also will produce oscillations when you apply input signal, but the oscillations will die out after some time. That's what it is called as under-damped system. Okay. The fourth type of system, that is called as over-damped system, where zeta value will be more than 1. That is called as over-damped system. Over-damped system. Okay, where zeta is greater than 1. So S1 is equal to minus zeta omega n plus j omega n square root of 1 minus zeta square having. Okay, remember this. Zeta square value is more than 1. You have to remember this. Zeta square value is more than 1. Okay, so that means you get negative sign inside that square root. So you get again a j, again one more j you will get. So because of that, okay, so we'll write this as zeta omega n plus j into omega n square root of, with minus n you can write down, zeta square minus 1. So you'll have minus zeta omega n. This becomes j. So j you take outside. J into j is minus 1. So minus omega n into 1 minus zeta square you can write down. S2. So zeta square minus 1 I can write down then. This will be zeta square minus 1. So both are negative numbers. This is also negative and this is also negative. So the whole value is positive, but minus sign is there outside. Over-damped system. So S2 will be minus zeta omega n minus j omega n into root of 1 minus zeta square. Here zeta square is more than 1, so you will get plus omega n into root of zeta square minus 1. When the first part is highly negative and compared to the second part. Okay, so second part is positive actually. So you will have another root. So roots are real and they are unequal. So roots are real and unequal. So when roots are real and unequal, the roots will lie on the real axis. One root will be lying here, another root will be lying here. So as far as our discussion is concerned, right? So S1 has more negative value, so it will lie here. And S2 has less negative value, it will lie here in our symbol. So this is 0. This is j omega axis and this is sigma axis. So this kind of systems are called as overdamped systems. Okay. So now based on the zeta value, now second order systems are classified into 4 types based on the zeta value, or 4 groups. Instead of types I will show here, I will say groups. Only second order systems are like this. So zeta is equal to 0 means it is, so zeta is equal to 0 means it is undamped system. Zeta is equal to 1 means it is critically damped system. Zeta is in between 1 and 0 means it is a underdamped system. When zeta is more than 1, then that is called as overdamped system. சொல்றேன் ஓகேவா? So most of the systems that we are using in practical for practical applications are underdamped system. Okay. இப்ப dampingனா என்ன அப்படினு கேக்குறாரு. So you go to a temple, go to any temple and you will find a bell. இல்ல சைக்கிள் பெல் கூட எடுத்துங்க, ஒரு பெல் இருக்கும். பெல் வந்து ஒரு மணி ஒரு இது இருக்கும், இது ஹேங் பண்ணி வச்சிருப்பாங்க. Just take your hand and make it to hit on this diaphragm, so it will make sound. And if you see the sound vibration and its amplitude, initially the amplitude will be greater. Amplitude of oscillation sound அதிகமா இருக்கும். டைம் ஆக சவுண்ட் ஆம்ப்ளிட்யூட் வந்து குறைஞ்சினே போயிடும், கொஞ்ச போய் 0 ஆயிடும். So whenever you have oscillations and if the oscillation amplitude of the oscillation is decreasing with respect to time, then this sound இல்லையா, சவுண்ட் இருந்தாலும் நான் ஏதோ ஒரு A of t அப்படின்னு எடுத்துறேன், ஆடியோ A of t, so that is decreasing. The amplitude of the oscillations is getting decreased. Now this is called as damping. சைக்கிள் பெல் அடிங்க, சவுண்ட் ஃபர்ஸ்ட்ல அதிகமா இருக்கும், அதுக்கப்புறம் சவுண்ட் குறைஞ்சினே போயிடும். That's called as damping. Right, systems also will produce, the underdamped systems will produce similar kind of output, not exactly this. So I'll make it clear and make it detailed in the next class. So actually our underdamped step response of the underdamped system பாத்தீங்கன்னா எப்படி இருக்குன்னா இப்படி இருக்கும். நாளைக்கு அதை டிஸ்கஸ் பண்றேன், இன்னைக்கு வேணாம். Okay, so we'll have more discussions on this underdamped system. இது மாதிரி இருக்கும். So damping means decrement of the amplitude of oscillations with respect to time. That's called as damping. புரியுதா? Undamped அப்படின்னா என்னன்னு கேட்டீங்கன்னா, the oscillations will be there but it will not reduce in time. That means the amplitude of the oscillation will not reduce in time. That is called as undamped. நாளைக்கு பார்க்கலாம் அதெல்லாம். ஓகேவா? So in control system we will not use A, we will use the symbol C. Just இத வந்து audio sound அப்படினு சொன்னதால I have used just A. Okay. So okay students, we'll meet tomorrow and we'll discuss the time domain specifications of the control system. Time constant அப்படின்னா என்ன அப்படின்னு கேக்குறீங்க. So time constant is nothing but, suppose assume that I have a system. I have a system. It is producing some output. Either or system. It is producing some output. Assume that the output is 1 volt. Output is 1 volt. Now, if it is a damping system or if it is not a undamped system, the output will be keep reducing like this. Keep reducing like this. Now, the maximum output is 1 volt and the output is keep reducing. At some time point, the output becomes 36% of 36 approximately I am saying 36.7% of the maximum. So it becomes 1 into right 36.78%. That is 0.368. So ஏதோ ஒரு டைம்ல அதனுடைய ஆம்ப்ளிட்யூட் வந்து 0.36 டைம்ஸா குறைஞ்சிரும். மேக்ஸிமம் எவ்வளவு வந்து மேக்ஸிமம் 10 இருந்ததுன்னா இப்போ 3.68 வோல்ட்டா குறைஞ்சிரும். மேக்ஸிமம் 1 இருந்ததுன்னா இப்போ 0.368 வோல்ட்டா குறைஞ்சிரும். அதுக்கு எவ்வளவு நேரம் ஆகுதுன்னு பாருங்க. That is called as time constant. So time constant is a measure of speed of response of the system. So time constant is a measure of speed of response of the system. Okay, va? Okay, students, we will discuss tomorrow. Witness, it is not 67.8, it is 36.8%. That means if you have a system and if system output decays like this, okay, now if the maximum is, for example, 1 volt, then the voltage at time constant duration will be 1 by E. So 1 into 1 by E. 1 into 1 by E. Maximum value into 1 by E. That is the time constant. Okay, va? Okay. Okay, students. நம்ம மீதி நாளைக்கு டிஸ்கஸ் பண்ணலாம். Bye.